Thank you. So I'm presenting on using UAVs or drones for doing horizontal and vertical documentation for stratigraphy and also extracting 2D line drawings. So my study site is the ancient city of Stobi in the Republic of North Macedonia. It was inhabited from the 3rd century BC to the 6th century AD and was the capital city of the Roman province Macedonia Secunda. It was discovered in the late 19th century by German scholars and has been continually excavated since that time. So this is the site in its current state of excavation, highlighting the test area that we used for this project. This area is currently being excavated through the Balkan Heritage Field School program, and we used it for our daily testing last summer, and we'll continue doing that this upcoming season. So there's 3 main objectives for this project. We wanted to find a low-cost alternative to manual stratigraphic recordings, an alternate to hand drawing, as well as collecting data simultaneously to record both vertical and horizontal information, and then to finally to automate the flight plans and the processing of this data off-site. So the drone we're using in the field is a DJI Phantom 4 Pro. It's with our lens pre-calibrated. It's drones don't always have the adequate cameras for this sort of recording, but with the Phantom 4 Pro, it's released a camera with adequate resolution. However, when you take the photos in the DNG format, there's an automatic geometric correction applied to the photos that causes a loss of information. So we're forced to use special software known as raw therapy to convert these photos into JPEGs. It's not very well known. They don't tell you that they've done this, and it's just automatically applied in all other software such as Photoshop and elsewhere when you're converting the DNGs, and you don't know that the correction's already been applied internally without a calibration sequence. All of our models are georeferenced using a Leica Total Station with a 1 arc-second accuracy, and we record points using these custom centroiding targets on the ground, which are automatically detected by our photogrammetric software. These are the parameters of our drone. We have our expected accuracy, looking at photogrammetric models only, of 1.5 millimeters at our height of flying height of 5 meters. But with our georeferenced models, our actual accuracy is 3 millimeters as per our control network. So this project I'm going to outline it for you in 2 phases. The first phase is what we did last summer during 2018. We did daily flights of the excavation over a 1-month period, using them with the camera pointed straight down in the nadir position. And then I will go over our second phase, which we started testing in the fall, and we'll be conducting this upcoming season. So the flight planning is done in a number of steps. The flight plans are built initially in DJI FlightPlanner, which are then exported as .csv files for a program known as Litchi, which allows the drone to fly automatically in a sort of lawnmower pathway without us having to interject with the flights. The flight plans are saved on the computer and then exported onto an iPad app, which essentially gets the drone to fly on its own from start to finish, as well as landing again. So what we did last summer, we would fly 2 flights per day with 98 images each in perpendicular to each other. So we'd have the flight paths running parallel to the walls of whatever building we were looking at, and then flying in a perpendicular direction to make sure we got full coverage of the entire area. So that would collect a daily amount of 196 images, which was then processed into a full 3D model of the excavation area. So from that result, we ended up with 3D models of each day of the excavation. These are just 3 examples of our ortho photos, starting from 25 June, which was the first day of excavation that season, ending on 19 July. And you can just visually see from these ortho photos the difference over the days. We have one for every single day of work. These can be useful for a number of analyses to determine the change from layer to layer at each level. And because we're recording it every day, we have documentation of every step of the excavation process. For example, we're able to compare the two 3D models to detect the empirical change, how much in volumes of dirt that's been removed. So we can have the volume calculation of a certain layer, how much was involved in that, as opposed to counting number of buckets you're filling. So in this model, we've compared 12 July to 19 July. So that was 1 week of difference. The red is areas with little to no change. And then the green is the middle change, and blue goes down to about 25 centimeters of removal. In the top right-hand corner, there's a room there, and we removed that. This was the difference from one floor level that was discovered 1 week to the next floor level the next week. And you can see where there's the more change in the unevenness of the floor. In addition to volume calculations for layers, we're also extracting 2D line drawings from these models. So we're replicating historical stereo-plotting techniques, drawing directly onto the 3D model for a fully interactive, accurate experience that reproduces these line drawings. And as we do this, we maintain the scale of 1:1 from start to finish, from the drawing in 3D to the notations that's done in AutoCAD to produce these final drawings. One of the reasons that we do the daily recording is to halt an excavation to produce these drawings takes days, if not longer, to do it by hand with pencil and paper. This speeds up the process, and the drawings are often done at the end of the season, days after the excavation's finished, as opposed to we can go back to weeks earlier to produce these drawings and to collect information about the layers that we had excavated. There are some limitations that we found with this nadir-only photography. And while it is very adequate for horizontal mapping and change detection, you get insufficient coverage on the facades of walls and stratigraphic bulks. And to add in these areas, we are forced to terrestrially add in terrestrial photogrammetry by walking along the walls with the camera, as is traditionally done for many of these practices, for the vertical recording. So I'm sure many 3D models, you see this on facades of walls, a sort of melting appearance and holes because of the severe look angle of the camera. And in addition to that, the photos are taken with a drone in landscape. And landscape photography does not take full advantage of the established programmatic principles of base to distance ratio. The second phase of this project involved changing the drone from flying forward to gather horizontal images. The drone now be flying sideways, and we were in portrait orientation, as well as the addition of what is known as the Maltese-Cross configuration to gather information at oblique angles for facades of walls and the faces of stratigraphic bulks. So to start with the portrait versus landscape, portrait photography has a better base to distance ratio for mapping and using stereo pairs. It also improves the Z accuracy due to the better base to distance ratio, and the Z accuracy is often the limiting factor for aerial projects. This means that by improving Z accuracy, we can fly a little bit higher, take less images, and still maintain the same accuracy. More strips, require more strips with these sorts of images, but there are less images per strip. This shows the comparison of the overlap that you attain in landscape versus portrait. It's portrait on the right. And as well, the equation that we used for calculating our desired overlap. DJI FlightPlanner works under the assumption that you will always be flying in landscape when you enter your desired forward lap and side lap of, we fly with 80% forward lap, 20% side lap. It calculates the positions of the photos automatically. to make up for that with the portrait landscape, we have to use this mathematical equation to calculate the inputted value for portrait, which will be manually changed in a later step. So this equation, L represents the resolution direction in the direction of the overlap, and the P0 is the overlap in landscape. So for our project with 80% landscape, forward overlap, we would enter 73% for portrait, and for our side lap of 20% in landscape, we would enter 40% for portrait. And as I said, this will essentially be forcing the drone to fly sideways. The second part that we're adding in here is called the Maltese-Cross. It's built off a camera configuration model where you have 4 cameras pointed in the 4 cardinal directions. It's a single system. But what we're going to do is have the camera move into these 4 positions on its own, as it's not possible to attach 5 cameras to one of these commercial drones. So we add 4 oblique images at each point in the 4 cardinal directions, in addition to the nadir image. At a flying height of 5 meters, we determined that a 45 degrees angle of the camera captures the facades, the walls, and the bulks. DJI drones can only take 99 photos in their automated flights, but this will take 5 pictures at each waypoint. So it essentially cheats that problem. It can be flown as a single mission, but I will discuss that as limited by the battery life and the size of the area they're looking to document. So our flight plans are still built in DJI FlightPlanner, still exported as a CSV, but what we're doing is we're manually editing the CSV file in Excel. This shows on the side underneath where it says heading, we manually change the heading from 215 to 145, which turns the drone and has it fly sideways. And we also add the additional actions of rotate the camera, take photo, tilt the camera, take photo, rotate the drone for these 4 oblique images. So what we get is 5 flights, each with 98 images, for a total of 490 images, plus our cross strips. So we have almost 1,000 photos every time we do this, but it gives us full coverage of the entire area. Our results of this give us full models of the excavation area or buildings. This was done at the excavated Theodosian Palace building. At the top, we have our nadir-only photography with the rocks melting into each other, and the bottom, with the addition of the oblique photos, we have very sufficient, accurate models that can be used for drawing and for stratigraphic analysis. This is an example of one of the long bulks in the excavation. We have the same problem at the top with the rocks melting into each other, and it's very difficult to differentiate between the different layers. And in the bottom, when you're zooming in, it's a little hard to see in this photo, but when you zoom quite in, you can see the lines where the layers are changing. So conclusions about this. So the daily UAV flight provides useful information about every stage of the excavation, and that can be revisited at later dates. This is very quick recording and completely automated. So once we build these flight plans over each area, we can move them all over the site and adjust the size to fit our desired excavation area, and the drone will fly and collect the images automatically. The addition of the Maltese-Cross simultaneously records the facades of the walls and eliminates the need for terrestrial photogrammetry. However, as I said, we're taking 1,000 photos in this configuration. It's an unmanageable amount of data for over 1 month if we're doing this every day. So what we plan on doing for this season is we're going to continue with our daily nadir flights and adding in the weekly Maltese-Cross at the end of each week, as well as the first day of excavation, or if necessary, at significant situations that are uncovered. And to acknowledge my colleagues from National Institution Stobi. And thank you.